All right, welcome to a lecture on data simulation. So sometimes you might want to simulate data because you want to try to either understand if your models are working like you think they are, or to determine appropriate sample size, for example, a power analysis, to better understand your data, or for many reasons. But simulating data is a thing that happens quite often in science. And R has 4 built-in functions for most distributions that you'll find useful when simulating your data. And they start with R, D, P, and Q. So for example, if you're using the normal distribution, it would be R norm, D norm, P norm, Q norm. And you've probably seen this in your time using R. And the R function is for generating random numbers from a distribution. The D is for the density, which evaluates a distribution at a certain point. P is for evaluating the cumulative distribution function for a given distribution, and Q is for the quantile function. And we'll discuss that in a little bit. So let's start with R norm. So R norm is sampling randomly from the normal distribution. And how you sort of specify that function is you put in how many numbers you want sampled, and then you describe the parameters of your distribution. For a normal distribution, you'll have a mean and standard deviation, but that will change depending on whatever distribution you have, whatever the parameters are. And if you ever want to know what parameters you need to specify, you can just do $R norm or $R poise for the Poisson distribution, for example, and on in R, and get the help page to come up. And so here, this code simulates 10 draws from a random normal distribution with a mean of 1 and a standard deviation of 0.5. And those 10 values have been printed here. And you'll see that if you do this twice in a row with the exact same mean and standard deviation parameters, you actually get different sets. So in the first 10, you get one specific set, and that's different from that second set. And so that brings in this set seed function. If you're basically every time you run an R norm or any sort of random distribution function where you're drawing from that distribution, R will pick a number to start with in its list of the seeds that it starts its random just draws from. But if you want to get the exact same result each time, which you might want to when you're doing simulations, if you want to make sure you have the exact same results every time, you have to set the seed. And so you do that by putting any number in the set.seed function. So you can see here, if we specify set seed at 10 for this random normal draws, then you can see you get the exact same values. And you need to set the seed before every time you enter that R norm function. And so one thing that can be really useful from simulating data, especially from the R norm, is to plot your distribution. Sometimes it's just nice to know what a distribution of a certain type looks like when you give it certain parameters. So say here we have a lot of draws from a normal with a mean of 1 and a standard deviation of 0.5, and another set of draws from a distribution with a mean of 5 and a standard deviation of 2. And then if you plot that, you can see that those mean distributions are really different. And, that might be fairly intuitive for a normal distribution because we're pretty comfortable with that one. But as you start to use more complicated distributions, sometimes being able to draw it or plot it will help you understand what a gamma distribution looks like when you have various different parameter types, for example. And so you can also use the p-norm function, and that calculates the probability of a certain point on the distribution. And so say you want to know what's the probability of everything up to the value of 2 from a normal distribution with a mean of 1 and a standard deviation of 0.5. And you can see here that that's 0.977. That's the output you get from this p-norm. And that's plotted here in the graph, basically saying since the area under the entire normal distribution is 1, if you're evaluating that up to 2, then that area is 0.977. And if you were to move that down a little bit, say you want to know what's the area under the curve, or the likelihood you could get up to 0.5, which you can see is on your x-axis, with a mean of 1 and a standard deviation of 0.5, the answer is 0.158, or 15%, basically 16%. And that's drawn here. You can also use the dnorm function if you ever need to find out what the probability is at any point. So that would be sort of thinking about what is the value on your y-axis, your density here, or that's your probability of getting a certain value on your x. And so if you use the dnorm and you want to know what's the likelihood of getting a 1 here with a mean of 1 and a standard deviation of 0.5, the answer is almost 80%, right? Because, and 1 is the mean here. So it's a really high likelihood that you'll get 1 out of drawing from this distribution. And we can do this at any point, so we can go back to that point we were looking at before for the p-norm, where what's the probability that you'll get a value of 2 for the same normal curve, and you can see that's a value of about 10%, 10.79%. And so that's where that green line crosses the y-axis. And dnorm is also helpful for plotting the distribution. There's many different ways you can plot the distribution with rnorm or dnorm, and all the code is under the hood to look at how to do this, but dnorm can be really useful. And finally, qnorm is the last one you'll think about. It's used to find the probabilities of certain quantiles. I would say you probably use this one the least, but it can be useful to know sometimes. So say you want to know what is the value on your x-axis for the 85th percentile of a normal distribution with a mean of 1 and a standard deviation of 0.5. And that answer is 1.5. And you can see that plotted here. And there's lots of other distributions you can think about, right? You can use the Poisson distribution. You can draw 10 numbers from a Poisson distribution, and the parameter you'll want to specify there is the lambda. That's sort of a spread parameter. You can do the binomial distribution, which and you specify there the parameters are size of 12 and probability of 0.2. That can be, whatever those parameters should be. You can also use a gamma distribution. And that has a shape and a rate parameter. And so again, if you want to know what parameters need to be specified, you just use the help function to figure out $r gamma. You can figure out what those parameters are. And I also recommend looking these up in Wikipedia, because Wikipedia will also describe what those parameters are, how they're defined with equations, and also what various distributions look like with various parameters. So this is just some examples of some of the functions you might want to draw, the distributions you might want to draw from, but there are many. And so some ways you might want to simulate data is based on small samples. So say you have a data frame here where you have your identification of your organisms 1 through 20, and they all have a mass and a sex, male or female. And if you group them, you can group them by sex and summarize the mean and standard deviation of your mass. You can see here that the females tend to have a mean of 20 and a standard deviation of 3, and the males have a mean of 17 and a wider standard deviation of 5.75. And that's how we summarize the data, and that looks like this. So here you have a histogram of the data that we have, right? Very small sample size, but you may want to know how if that data was representative of an entire population, what would that look like? Because these distributions are pretty small. And so you could sample from a normal distribution, assuming mass is normal. It's often normally distributed. And you could set your seed for 100 for females, and you could draw 1,000 draws from a normal distribution with a mean of your data from before, that 20.6, and a standard deviation of 3. You could do the same for your males, where you draw a bunch of times from a normal distribution with that same mean and standard deviation that you calculated from your data. You could create your data set and plot it, and it would look like this. And again, this gives you a better idea. There's more samples here to look at. And so you can see that it does appear, if your data set is representative of the entire population, right? If that sample is representative of the population, then it appears that your females have a larger mass but a smaller deviation in mass, and the males have a smaller mass but a wider variance. And you may also want to simulate from a linear model, for example. You may want to simulate from a specific model instead of from a distribution of random numbers. So say you want to simulate from this equation, which is a pretty standard equation where y equals beta naught plus beta 1 times x plus some error, standard linear model. And here you can make the assumption that your error is normally distributed with a mean of 0 and a standard deviation of 2. And you can specify this in any way you want, given what you know about your system. And then you can give your beta 0 and beta 1 parameters values, here are 0.5 and 2. And then again, you can set your seed. You can simulate 100 draws of your predictor variable, x, from a normal distribution. That's a standard normal. So when you don't specify the mean and variance, it will be 0 and 1 for mean and standard deviation. And then you can simulate your error, right? So likely there's going to be some error around your predictor variables, and that has to be the same number. You have to simulate the same number as you did for your x. So 100 draws from a mean of 0 and a standard deviation of 2. And then you calculate response variables with that. So you can basically solve that equation, right? So beta naught is 0.5 plus beta 1 times x, which is 2 times the x vector, plus for each of those values, some error that you've simulated. And then you get a vector of y's. And here you can see the summary of your y's. That's what that looks like. And you can plot them here. So you can see now you have a linear model, a linear relationship between your x and your y variables with some error that you've specified. And you can do this with other types of distributions too. So you could use the same model, but instead have your x's be distributed as a binomial variable, either ones or zeros. So again, set your seed, and then now we'll simulate the predictor variables x. So here we're going to sample from a binomial distribution instead of a normal. So 100 draws with your two parameters as 1 and 0.5. And so when you look at that, you can see that you have a bunch of, basically a list of a vector of numbers for 0 and 1s, because that's what binomial is, zeros or 1s. And you can simulate error around that like before. Draw your error from a normal distribution of 100 and 0 and 2 from your normal distribution. And then you can calculate your y's again the same way, where you have that linear model, but now your x is no longer normal, it is binomial. So you have 0.5 plus your beta 1 times x, so 2 times either 0 or 1, plus some error that you've drawn. And you can get a distribution that looks like this. And this is your figure, right? You have zeros and ones. And you can also simulate generalized linear models with a Poisson distribution. So you may also want to simulate from a model from something other than a normal distribution. For example, say you want to use a Poisson log linear model, which is often good for count data. And here your y's are a function of Poisson distribution of mu. And then that log mu, because it uses sort of that log link, the log mu is a function of beta 0 plus beta 1x, where beta 0, again, you can specify as 0.5 and beta 1 is 0.2. Again, set your seed so you know you're getting the same numbers every time. Simulate the predictor variable x, which in this case is drawn from a normal distribution, but then you need to log transform that. So you have to take the log mean for the model, so you can run that through the Poisson. So that would be 0.5, right? Your beta naught plus beta 1 times x, 0.2 times your vector of x's, and that gives you a vector of log mu's. And then you can put that into your Poisson distribution, where you take 100 draws from the exponent of log mu. And then you can plot that here on as your x's versus your y's. And so that's some ways to sort of start getting an idea of how you might want to simulate data. And again, all of your own simulations are really going to be based on your own specific case. And so understanding the basics of how you actually simulate data from different distributions and what those different functions can tell you, and then also how to potentially start putting those into different formats where you have linear relationships binomial relationships, etc., can be really helpful when you're simulating your own data.